Great, thank you. So, Jennifer Golbeck or Jen Golbeck, I believe you prefer to be called Jen, am I right?
It's a little less formal, yeah.
Okay. Is a professor at College of Information Sciences at the University of Maryland, my alma mater. Her research focuses on AI and social media, privacy, malicious social media behavior, and trust on the web. She has a PhD in CS from University of Maryland and degrees in CS and economics at the University of Chicago. With that, I'll let you take it away.
Great, thanks. Nice to talk to all of you. I'm at the University of Maryland, but I've been quarantining in Key West, and so I feel like you all and I have the best weather in the country right now, probably. So it's good to be with you. I'm going to talk today primarily about some research on bots that I've done, detecting bots and sort of the universe surrounding that. But my interests in this space are really broad in terms of just bad stuff people do online, social media in general, AI and algorithms. So if there's stuff that comes up that you're interested in that space, feel free to chime in with questions, or, if we have Q&A time at the end to talk about anything in that space. So there we go. So I want to talk about bots, and particularly fake-like bots. So let me actually slide this guy up here and talk a little bit about this first, just to give us an intro. So bots obviously are an issue. We've been really focusing on them in the last 4 years, like since the 2016 election. They were around for a long time before that, but they gained new prominence at that point. And so there's a lot of really good and interesting research on bot detection that's out there. This is from Bot or Not, one of the bot detectors at Indiana University. And you can put an account in there, and it uses a bunch of different features to try to detect if something is a bot. So this is my Twitter account. I don't look too bot-like, thankfully. And it'll look at your social network, how often you post, what do you say, what's the sentiment, what kind of stuff do you talk about, and come up with this. And so that's been interesting. And we've done a little bit of work in my lab on bot detection, but we were more focused on sort of the implications of bots as opposed to, getting really in there and building detectors. And in 2015, I guess, I was on sabbatical and was like going to the grocery store, listening to Radiolab, and they had this episode on Benfords Law, which is fascinating. And I'm going to talk about what it is in a second. And it's one of those things that like stuck in my head, and I couldn't stop thinking about it for like a week. All I was doing was like thinking about this thing, which is a sign to me usually that it's something I should probably be doing some research on. And so it took me into this space, kind of unintentionally, of looking at bots more in depth. So I'm going to use that to take you through the work that I'm going to present today. So Benfords Law is basically a law of the distribution of first significant digits, which is a fancy way of just saying the first digit in a number. So if your number is 278, 2 in the 278 would be the first significant digit. And the story behind Benfords Law is that Benford was in the library with a book of logarithmic tables, and he found that the front of the book, which has the logarithms for numbers starting with 1, was much more worn than the back of the book. But if it's a book of logarithmic tables, you would think, I think the intuition is always that people are going to be looking up logs of numbers that start with 1 as often as they're looking up logs of numbers that start with 9. And so why would the front of the book be more worn than the back of the book? So that was sort of the first clue. And Benford was not the first guy to discover this, but he's the guy who gets credit for it. And so he went through and found that the distribution of first significant digits is in fact not equal, that there are not the same number of numbers that start with 1s and 2s and 3s and 4s all the way through. In a lot of naturally occurring systems, there's actually a distribution, and you can see it. My chart here is probably rotated 90 degrees from what you're used to, but we have the first significant digits here on the y-axis, and you can see that there's this pretty consistent curve. There's actually a formula that you can use to derive the frequency of first significant digits with Benford's Law. So if you're looking for a first significant digit of n, how often should that occur? You just do the log of n plus 1 minus the log of n, and that gives you the frequency. So for example, how many digits or how many numbers would start with a 1? It would just be the log of 2 minus the log of 1. That gives you about 0.3. That's how often ones show up. So Benford's Law, it works regardless of what base number system you're working in. So we're obviously going to be talking about base 10, but other than binary, you can use it for any other system, and you just change the base of your log to get that frequency. And it's pretty robust. So Benford's Law, Benford showed, and people who have done research since then have shown that Benford's Law holds for, like, if you take the distance of all the rivers on Earth, regardless of what unit you measure them in, they will follow a Benford's Law distribution. About 30% of them will have a length that starts with a 1, and about 5% of them will have a length that starts with a 9. And there's this nice distribution that you can see here. Surface areas of lakes, atomic weights, and one of the places that we see it studied now most often is in accounting. So Benford's Law is so reliable in looking at accounting that it's admissible in court as evidence of financial fraud. So if you take your tax returns and you just write down every number on your tax returns, it doesn't matter what box it's in, just write all the numbers down, about 30% of those numbers are going to start with a 1, down to 5% of them starting with a 9. You can do this with magazines, for example. Just take every number that you encounter in a magazine or like on a page of a newspaper. They'll also follow this distribution. So the accounting piece of it has been really interesting because people do use it essentially in forensic accounting investigations. And the kind of logic behind that is that if I'm faking numbers on my tax forms, I may be like, oh, I haven't added a bunch of fake numbers that start with 7s. I better put some more 7s in. So we as humans try to kind of balance out what the first digits look like. And so we make things that don't actually look natural because this natural pattern is not what we intuitively expect. And so the episode of Radiolab that I listened to was talking about the use of Benford's Law for detecting fraud in accounting, which I thought was really interesting. And I don't do any work on accounting, but I couldn't stop thinking about it. And finally, after about a week, I was like, okay, well, I do work on social networks. Maybe Benford's Law works on social networks. And so I kind of dove into this project that consumed like my every waking hour for a couple months, where I wanted to see on all these different social networks, does Benford's Law hold in terms of the network structure? So I'll get to that in a second. So we can just look at the graph here right now. So you can see on the bottom, I have a legend there. And so essentially each color in this bar is a different social network statistic. So the red is the number of followers people have on Twitter. The orange is Pinterest, but only part of Pinterest, and we'll talk about that in a second. So that's how many followers would I have on Pinterest. Twitter friends, so that's people that I follow on Twitter, is the yellow, Facebook is the green, Google Plus is the blue, and LiveJournal, old school blogging platform, is the purple. And so what we're looking at here obviously is social network statistics for the entire network. So in some cases, we were able to just randomly sample the network. At the point that I gathered this data, with the Twitter API, you were able to request the friend count and the follower account for any Twitter account given its ID, which is a numeric code, as opposed to its screen name. And the IDs were consecutive numbers. And so we were able to just kind of increment by like 10,000 and spend 2 months pulling down a sample of tens of thousands of Twitter accounts to get these numbers. Pinterest had some data sets already available that were quite large. Facebook, we were able to do a similar kind of thing to Twitter. It was a smaller data set because they're much more restrictive on how they share their data. But we could still use that numeric code and get counts that way. Google Plus had some data sets available, and LiveJournal, there's lots of archives of that data out there. So all of these, essentially, we were looking at friend counts. And what you can see here is that friends and followers, they follow exactly the pattern that Benfords Law would suggest. There's very little variation, and statistically they match up really nicely. Pinterest was an interesting thing though. The Pinterest number that we're using here is followers. So if I have a Pinterest account, how many people follow me? You also can, I mean, obviously you can follow people on Pinterest, but when we looked at how many people do I follow, the count of people that I'm following, it didn't adhere to Benford's Law. It looked sort of like Benford, but there's a big spike in the number of fives, which it looks exactly like fraud normally looks with Benford's Law, where it's like, oh, people have put in a whole bunch of numbers that start with this. Why would that happen? And so I dug into that, and it turns out that when you sign up for Pinterest, when you register the first time, it automatically follows 5 people for you. And then you can go in and follow more, but a lot of people don't. They just come in and they're searching for ideas or recipes or pictures, but they're not interested in following people per se. And so lots of people just have the default number of 5 people that Pinterest automatically followed for them. And so it is a kind of fraud in that it's not a naturally occurring pattern of human behavior. Pinterest did this, and so it doesn't follow Benford's Law, but in a way that sort of proves that Benford's Law should hold. It's this one artificial thing that's done that kind of makes it deviate from the pattern. So this was super exciting. When I had all of this data, I finished the collection all at once, and then it's really quick to like run this through and do the check. It's one of those like most exciting moments of my research career where it's like, I know this thing that nobody else knows, and it's like super cool and really exciting. So that was like great fun for me. I loved doing this project. And I thought, it's just interesting scientifically to be able to come and say, look, these online social networks are also adhering to Benford's Law. That's a thing to know. But I wanted to kind of delve into the data a little bit more deeply. And so the numbers that we're looking at here in this chart are for the networks as a whole, right? So we have 50,000 Twitter users, and we're looking at their follower counts and their friend counts. And so it's sort of talking about the network as a whole. But the next natural question would be, does it work for individuals? So if you take me, I have a Twitter account and I have whatever, 20,000 followers, and I follow, say, 1,000 people. So if we just take my 20,000 followers, they all have a count of how many people follow them. So if we take the pool of my followers, will their counts also adhere to Benford's Law? So we're not looking at Twitter as a whole, we're looking just at my followers. Do they look like Benford's Law? Now, on one hand, you might say, sure, they might, because if Twitter as a whole follows Benford's Law, and then we're sampling from a whole that has a population that follows Benford, then the sample should also follow Benford. On the other hand, it might not follow Benford because social networks, the people who follow you on a social network are not randomly sampled from the whole population. They we spent all of this research finding out that like people don't just randomly follow other people. There's meaning behind that following. They're coming from communities, they're likely connected to each other. And so it could totally be the case that since I'm not randomly sampling from the whole Twitter population, that I get a group that doesn't look at all like what Benford's Law would suggest. But it turns out it does. On all of these platforms, if you look at egocentric social networks, you take an individual and their friends or followers, and then you look at the counts among their friends or followers and do the first significant digit analysis, it also follows Benford's Law. So it works for the networks as a whole, and then it also works for egocentric social networks. And we were able to show this for probably 100,000 accounts across different platforms altogether, that almost everybody adheres to what Benford would predict. So that's pretty cool that it works like for the network as a whole, and then it works for individuals. But of course, it's not going to work for everybody, right? There's always variation in these kinds of statistical patterns, and people will not follow Benford's Law for all kinds of non-sketchy reasons. So I was interested in, what does that look like? How many of these people actually are adhering to Benford? Once they start to deviate, what does that look like? And so for Twitter, the nice thing is that we were able to look at all these accounts. We were able to take the numeric IDs that we use to do our sampling, convert those to screen names, and then actually go look at what was there. And the vast majority of Twitter users look either statistically identical to Benford or very close. Like there will be a little variation where your statistical test might say that it's different, but it looks pretty much the same. But when we sorted it by like most Benfordy to least Benfordy, there were a handful of about 120 accounts at the bottom of the list that didn't look anything like Benford. And I was like, okay, well, like, let's take a look and see what these are. And this is what they are. They all looked exactly like this. I I basically discovered this weird Russian botnet. All of those accounts at the bottom of the list were tweeting exactly like this. So it was the same controller, the same app producing tweets for all of those accounts. They were tweeting in Russian. When you translated it, the text was essentially excerpts from either technical manuals of novels or novels. It wasn't always complete sentences. This one happens to be a complete sentence, but sometimes it would just stop in the middle. So, who knows, they were maybe just using a character limit. Once you hit the end of a word, you'd stop. But they were all identical. They had the same. This one doesn't have a profile picture, but most of them at the time did. A lot of them have been shut down now. They would have the same use of emojis that would pop in there, stock photos that would show up in places, clearly, and we were able to identify later, controlled by the same app posting for them. What were they doing? I don't know. They all just tweeted this, and we followed up with them since, and like I said, a lot of them have been shut down, but the ones that are still there haven't tweeted in a couple years, but they still look like this. They haven't suddenly switched to doing something else. So why should there be this network? I don't know. I've never been able to figure it out. We detected about 120 of them by doing just this random sampling, right? We randomly sampled, I think, 50,000 Twitter accounts. We found about 120 of these Russian bots that clearly violated Benfords Law. 120 out of 50,000 is kind of a lot of Russian bots all controlled by the same. And then I eventually went out and crawled them because they tend to follow each other. That's part of what makes their following patterns unnatural. And this network was about 100,000 bots large that we were able to detect just by crawling and looking at the apps that were posting. And it never did anything nefarious that we could tell. It wasn't posting spam. It wasn't responding. The only thing it was retweeting was basically each other's tweets. So I have no idea what it was, but it's interesting that I absolutely did not set out to look for bots and ended up finding a whole bunch of bots, and in fact, a very big bot network, by looking for violations of Benfords Law. So I just wanted to show that it held, and when I looked at what was violating it, it turned out to be bots, which is exactly in line with like what all the research has said, though I hadn't even gotten that far in my thinking, that violations of Benford is often an indicator of fraud. And in fact, what fraud would mean in social networks could potentially be a bot. And that's exactly what I found. So that was pretty interesting. I was really excited by this research. I published it, I think late in 2015, maybe early 2016. And then, spent about a year just trying to track down this botnet and figure out what it was doing, could not figure it out. But along the way, started thinking about, okay, so if I want to actually use this with respect to bots, how might I do that? And that essentially raises this question, like, what does fraud mean in social networks? So it could be a bot like this, but what are other kinds of fraud? And so that got us to the idea of fake like bots, but that also includes retweet bots and all of these bots that you can hire to basically interact with you. They can follow you, they can retweet you, they can like your stuff. It's really easy to get these. So you can buy likes or shares or followers. It's really cheap. It's about $1 for 50 to 100 likes. I funded this research myself. I think I paid like $50 and got thousands and thousands of likes for all kinds of different tweets. And so that seemed to me like a different kind of fraud than having a botnet, because the fraud, while it is bots that are doing it, is on individual tweets or Facebook posts as opposed to an account that's getting followers. So I'll come back to that. So I wanted to look at, can we detect when these bots are interacting with content? And so we looked at this both on Twitter and Facebook. On Twitter, I created a bunch of tweets on a burner account. There's nothing in the tweets. I think I just tweeted like the number 1 and then the number 2. nothing that anyone would actually interact with. And then I bought 100 retweets for 142 of those fake tweets or stupid tweets that I made, just numbers. 140 of the 142 violated Benfords Law. And I'll talk about the statistics in a second, but that's what that p-value is for. So when I bought the retweets, almost every single one of the tweets, if you looked at the first significant digit distribution of followers of the people who retweeted it, so essentially we have to find that number. So we look at who retweeted this, we look at their friend or their follower counts, and then we analyze the first significant digits. It didn't look natural, that pattern. On the other hand, if we took tweets that had over 100 retweets that came naturally, so these were from, say, popular accounts or things on current issues where we know they would naturally get that kind of traffic, most of those had a first significant digit distribution among the retweeters that did follow Benfords Law. Only 20 of 147 tweets that we used as a sample violated Benfords Law. So that's pretty strong evidence, not that Benford is like a perfect detector, but that if you look at an individual tweet and then the counts, either the friend or follower counts for the people who interact with it, you generally would expect it to follow Benford's Law if that's a natural pattern, and you generally would expect that it doesn't if it's fraudulent, essentially purchased retweets. We did the same thing on Facebook. This was much harder because Facebook is like such a gatekeeper to these accounts. They really try to shut stuff down, and it took us forever to get 67 Facebook posts put up to get that kind of interaction. But we were able to buy likes for those, again, for the same price, a couple dollars, to get hundreds of likes. And when we bought them for our Facebook posts, about 77% of them violated Benford's Law. If we looked for posts that naturally got likes, 38% of them also violated Benford's Law. So the majority followed Benford's Law. It's not quite as good a detector on Facebook. And I have some theories about that in terms of how people actually set up their networks, like how you connect with people on Facebook. But it's still a pretty strong indicator in there. So that's all to say that when we're looking at a different kind of fraudulent behavior, essentially purchasing fraudulent interactions, both on Facebook and Twitter, applying Benford's Law to the people who do those interactions generally is going to give you a pretty good idea of if they're fraudulent or natural. It's not a perfect detector by any means, but it's something there. For those who are interested in the statistics, let me just get into that here really briefly before we move on. So, if you want to do stats with Benford's Law, it depends what kind of question you're asking. There's a lot of different tests that you can do, but here, we weren't really looking for, is this a perfect match to like the exact numbers that Benford would predict, but rather just trying to get a general guess, like how close is this? Like, is it Benford-y or not? So we just use a simple chi-square test. We let the p-value be a measure of how well a distribution adheres to Benford. So we weren't actually looking for statistical significance here, even though that's what you would use a p-value for normally. But if we got a p-value that was less than 0.05, we said, well, that's a strong sign that the pattern is deviating from what's expected from Benford. We don't actually care about the statistical significance part of it, but it is a useful threshold to say, okay, this doesn't really look like the Benford distribution. And so that's where the p-value came from. Doing stats here is just tricky because you're taking so many samples. Here we're looking at hundreds and hundreds of tweets or Facebook posts. And if you want to correct for that p-value to get real statistical significance, you're not going to get great results that way. And also, we don't actually care about statistical significance here. We're much more just looking for patterns. Is this a useful detector? So we did use a p-value, and we use that standard 0.05 threshold, but I just want to be really clear that it's not significance that we care about here. It's more just, how good a fit is it? And the p-value gives us a good indication of that. So, so why do people do this? Why do people buy likes and retweets and followers. I think for the reasons that we've seen in a lot of the bot research that goes on, power, influence, legitimacy. So if you have an account and you have 100,000 followers, you look more legitimate than if you have 1,000 followers. And if my 99% of them are fake, you still look more legitimate. Fake Famous is a documentary that just came out, I think on HBO Max, maybe, like just in the last couple of weeks. And it's about essentially making influencers. Like, can we take 3 kind of random people and create this influencer profile for them? And it included buying a ton of followers, and it worked for one of them. Like they bought thousands and thousands of followers, they bought fake interactions, it made everything look legitimate. And for one of the people who was an actress, it was enough to kind of help her in auditions and get her seen and get people sending her free gifts and everything. So those numbers, because they're the easiest way for us to assess something on social media, carry a lot of meaning with them, and they carry legitimacy and influence and kind of an idea of power, even if they're artificial. And in fact, a lot of it is artificial at this point. And of course, we've seen this in politics as well, that you can have kind of extreme positions that normally would be shut down. But if those extreme positions, say, show up in a tweet and the tweet gets 50,000 likes and a lot of comments on it, it looks more legitimate than just some crazy guy saying something stupid. And the bots are there, these huge bot networks are out there to help kind of amplify those ideas. So that's why we see people doing this. I will add that on Facebook, a lot of the fake likes that I saw being purchased, just as I was skimming through, not doing the Benford analysis, but I would look at the people that I had identified as bots that were generating fake likes and look at the other stuff that they liked. A lot of it was like teenagers, mostly teenage girls who would post pictures of themselves and then would buy likes for it. I think because it allows you to say, like, look, this picture of me in my dress or this picture of me at the beach went viral. People really liked it. And it conveys this sense of like popularity, or like outsiders like me. And it was a thing that made me really sad to see, these 15-year-olds buying hundreds of likes for their pics, not for influencer accounts, just like for their regular Facebook account, I think, to show it to people. So this idea of, buying legitimacy is a thing, that I think manifests in a lot of what I saw. And I can talk more in depth about what some of those accounts looked like if we want to at the end. So is there a solution that lies here in using Benford? It can be gamed for sure, but it highlights a strategy. So currently this sort of pattern is not used in bot detectors, at least not as far as I know, but it could be. And of course it raises the question, well, couldn't bots just make follow people in a way that they'll adhere to Benford's Law? And sure, they could, like, you can game that. But the fact that Benford's Law works in any base system, right? You can use base 8, base 16, base 12, whatever. Benford's Law would still apply, makes it a little trickier to game it. If you're just working in base 10, you can say, okay, well, here's the distribution I expect. I'll add in, another person with a 4 and a couple more people with 1s, and that's going to look like what we expect. But if you have to make it work so that it's also consistent with Benford in base 8 and base 12 and base 16 and whatever else, that becomes a lot of engineering work, which probably is too much for people, who are building these botnets. So I think it's a strategy there. This may be part of the standard escalating arms race like we had with spam and that we now have with bots, and that it's hard to try to detect this stuff. And once you come up with a detection method, they come up with a way to thwart that and so on. But it's a very straightforward statistic to calculate. You don't have to do a lot of work. And it's something that you can, easily do in a few different bases. And we know that it's pretty reliable. And so it becomes, I think, an interesting feature that can be included in the set of things that are now used to help detect bots. So before I kind of wind up, I do want to talk about how this came to really bite me at the end of last year. So I had done this work, and I've talked you through a couple of papers that I did. And now, I guess a couple years ago, probably a year and a half ago, I got contacted by Netflix. They have this show called Connected, hosted by Latif Nasser, who actually is on Radiolab, where I originally learned about Benfords Law. And the show Connected is sort of a travel slash science show, and there's, I think, 6 episodes, and each one looks at a different idea, and he travels all over the world and talks to experts about the idea. One of their episodes was on Benfords Law, and so they were looking for Benfords Law experts, and so they had me on the show, and I talked about all of the stuff I just talked to you about in a much more accessible way. And that, I think, came out in July. Connected came out on Netflix. So it's a beautiful, wonderful, happy, family-friendly show. So if you're looking for science stuff to watch, aside from the fact that I'm in the one episode, it's like really great, and Latif is just a charming, wonderful guy. But it brought the idea of Benford's Law much more into the public view than it had been before. And everybody kind of learned that Benford's Law is a thing that helps detect fraud. And what is the biggest kind of fraud that people were really trying to detect in the last few months? It was all the Trump supporters trying to detect fraud in the elections. So they said, well, hey, this Benford's Law thing detects fraud. We're going to use it to show that there was fraud in the elections and that Biden didn't win. So they took the precinct level vote counts for all the candidates, but basically Trump and Biden, and they ran Benford's Law on it, and it doesn't really look like Benford's Law. And so they said, okay, it's fraudulent. And so my life for about 3 weeks became shooting down Benford's Law conspiracy theorists, because, like, on one hand, it's not a dumb idea to say, like, let's apply this. On the other hand, it's one of those things that highlights the fact that you actually have to be better at math and science than what you can learn on a Netflix show to apply it correctly, right? You can't just watch watch Netflix build a spreadsheet and do science, right? It takes a little more work than that. So here's why Benford's Law doesn't work for elections. One is people have been trying to use Benford's Law on elections for like 20 years and it doesn't work. We know that it doesn't work. And so, for all these people to come along and say that they're proving election fraud when it's documented that Benford's Law doesn't work on elections, that's troubling as a scientist, right? That you haven't done your lit review at all. On top of that, one is that Benford's Law requires independence. So if I'm looking at friend counts, those shouldn't be dependent on anything else. But vote counts in a precinct are very much dependent, especially when you have 2 candidates. If there's 2,000 people in the precinct and there's maybe a third party candidate, but they're not getting much of the vote at all. So essentially we have 2 candidates. If you have 2,000 people in the precinct, if 500 of them vote for Trump, then 1,500 of them will have voted for Biden. Their vote counts are dependent on each other. And so that violates one of the core principles that we know is necessary for Benford's Law to apply. The other is that Benford's Law generally has to span several orders of magnitude. So if you just have, say, numbers from 100 to 1,000, you're in one order of magnitude, Benford's Law generally isn't going to work. It's interesting and useful and essentially works because it often almost always spans many orders of magnitude. With precinct counts, you're usually within one order of magnitude. Precincts are all generally the same size on purpose because you don't want to have a precinct with 2 people and then a precinct with 20,000 people. So if you're looking at the city of Chicago data, precincts I think are about 1,000 people. And so you maybe have some numbers in the hundreds and some numbers in the low thousands, but you're not spanning lots of orders of magnitude. And so it doesn't work. Benford's Law doesn't work in those situations. So these 2 really core things that are required for Benford's Law to apply don't apply in elections. That said, if you tell people this who feel like they have proved that there is fraud in the election, and then you explain the science to them with lots of citations, they get very mad at you, and they sometimes make death threats to you, and they call you all kinds of names on the internet, especially if you're a woman. And so it was a very interesting part of the post-election cycle for me. to the point that where I feel like this is a nice way to wrap up the story, that Latif Nasser, who had done this show on Connected, and we follow each other on Twitter and we kind of talk on the phone every now and then. He's like, well, we should talk about this. And so Radiolab did a follow-up Benfords Law episode that interviewed me, that talked about this and election fraud, and why it doesn't work, and talked to some other experts there. So where I first encountered this idea on this weekend NPR show that got me into all the research that I just talked about, is where I have ended up with it, coming back onto that show myself and talking about how in fact you can't use it to detect fraud in the elections. In fact, when you do apply Benford in the way that may work, which is using second significant digit analysis and a whole bunch of statistical corrections, what you do find is that there wasn't any fraud. So if you do actually do the math and the science correctly, you come out with the example, with the answer that I think we all would have expected. So with that, I think we've got plenty of time for questions. Keith, I don't know how you want to handle that, if you want to do like chat or just have people unmute themselves.
Oh, thank you. Yeah, we were actually the way we're organizing it now is that we're going to allow people to use the chat to send questions. But first, Alma, would you be able to allow people to use the chat once any trolls have been removed? And also, they'll post a message, and either you or I could read out the question, and then you could answer. So Alma,
Yes.
have you opened up the chat?
Let me do that.
Okay.
Chat. Can people see the chat? Can somebody do a quick test?
Since I'm co-host, I can use the chat either way.
Yeah.
Can someone else confirm that that they can use the chat? Okay, great. It looks like it works. So with that, does anyone and everyone have questions? Feel free to post them.
I'll say thanks to Tyler. I gotta say, like, I do a lot of kind of random research in addition to like my core stuff. So like my core research is really about like building algorithms to like find out personal traits of people from their social media data. But that's probably 40% of what I do. And a lot of the rest of it is just interesting stuff surrounding it that I like. And so, I've got these papers on Benfords Law, and it was like so exciting and fun. But I've also done stuff on like pets. I've done a bunch of research on pets on the internet. And like, I like just being able to do stuff that you think is cool. Like that's one of the best parts of being a professor is you can do whatever you want as long as it's interesting. And that sort of took me to this place, which has been so rewarding.
I gotta agree with you there. As you can tell from my profile, I love dogs. So maybe that's something that we'll be able to briefly mention in our afternoon talk. But in the meantime, I should mention that Emilio Ferreira has asked a question. Now, Emilio Ferreira is actually one of the people who helped invent the botometer or botnet. So he would be very relevant with respect to misinformation. And he said he loved the talk and the Connected episode. And he has two questions. First, how generalizable is this framework? And also, does it capture, in addition to the kinds of models we built that incorporate a lot of, Also, what does it capture in addition to the kinds of models we build that incorporate a lot of network dimensions?
Yeah, I think this probably will supplement the kind of network data that you already have, because I don't think there's anything wrong with the current models for bot detection. I mean, they're very good. I think this is an interesting other feature to put in there, because it captures something a little bit different. Like the network patterns that are currently used in bot detection are incredibly useful and like make logical sense. This captures something beyond that, I think, which is these sorts of patterns where even if they try really hard to include follow a lot of other people or include non-bots in those lists, they do it in a way that often ends up being unnatural. Again, we haven't done like a big scale study looking at like the precision and recall of this. I've got the data to do that, so it's like next on my list. But having done like a quick analysis of it, probably 3-ish years ago, maybe 4 years ago, I took a lot of bots that we were able to detect with just using Benfords Law and put them through the bot or not detector and a few other ones. And a lot of them weren't caught by it. And so it tells me like there's some other dimension that's being captured there, that there's just something in the way that they do their network structure building that Benford's picking up that the other measures aren't. But yeah, I spent a lot of, I guess, the summer doing data collection from a lot of the data sets that are, in the IU repository, actually getting these counts from there. So one of the like to-do projects, once my motivation comes back, maybe when COVID is done, or maybe a little before, I hope, is to get in and actually get some precision and recall numbers, where we've got a lot of labeled accounts, and we can do this, on a big scale, because that was a tricky thing for us. We didn't have that, and so now we have that data, which, by the way, I'm submitting a web science paper on that, I guess next Thursday. So if you want any of that data, just like, numbers and things on these bots, I'd be happy to share that with you too.
That sounds very fascinating. And also, I was thinking about, I've heard vaguely that Twitter bots are getting more and more sophisticated about evading detection. So potentially, we could see how well this works also in comparison to other Twitter or other bot detection over time. Anyway, so the next question from David Zhang is, Jennifer, do you think the connections of a man-made chip obeyed Benford's Law? For example, an Intel Atom chip is over 20 physical layers. There are many connections per layer and connection between layers by connectors. Since they're man-made, I wonder if they would obey Benford's Law. Do you have any insight on that?
So definitely man-made systems follow Benford's Law. I think so. I don't know enough about the structure of those to like give you a really confident answer, but I will say that we often see Benford's Law being followed in systems that have a power law distribution. Not always, but we, in social networks, we see this. If you map out like follower counts, you get this really nice power law distribution. When you have that, it's a good sign to test for a Benford's Law distribution. So I don't know enough about chips and the connections between them to know it. I would suspect that they follow that, since so many networks do. But you may know better than me. So if they do, like if you were to map out the counts of connections, and that would have a power law distribution, I think it would be a good thing to check for Benford. And I wouldn't be surprised if it followed it in that case, but I don't have enough domain knowledge to give you a confident answer.
So speaking of which, I mean, that also agrees with my understanding of Benford's Law, that it depends on whether distribution is power law or not. So I guess in a more general sense, a more generalized Benford's Law would be different if you knew the data was roughly Gaussian distributed compared to power law. And if your data was log normally distributed, naturally your Benford's Law will differ. Am I correct?
Yeah, that's exactly right. And I think if we've got, it makes sense, right? If you have like a normal distribution, of course, everything's kind of clustered around the mean. And so whatever digit that has, like that's going to be, the numbers around that are going to be more common. I don't know if there's a sort of parallel to Benford's Law that you could generate with sort of like mean and standard deviation if you have a more normal distribution. But yeah, I mean, your intuition is exactly right.
Okay, thank you. Do others have questions? Okay, let's see. Let me look at questions I might have.
I will say someone did mention that my dogs are Twitter famous, which they are. They're like way more famous than me, and they were in the Netflix show. So I put their social media handle in the chat if anyone wants to check them out. They're much more exciting than I am.
Yeah, I was noticing it's like 100,000 followers. Like, that's the thing. Like, my dog is so photogenic. I feel like I sort of pale in comparison.
I teach a class on how to become an influencer on social media. So if your dog wants a consult, I'd be happy to provide one.
You know, I'm gonna make my dog Twitter famous now. But anyway, so let me think. Yeah. So with respect to actually the voter fraud, I thought that was quite interesting that there are people who are trying to use Benford's law to that purpose. Do you have so you're mentioning, okay, that correlations between numbers violate Benford's law, or the fact that the magnitudes are small and violation of power law. Um, are there sort of is there a way one could tackle these conspiracy theories? Like, what would be the what is the exact list of things? So they have to be independent and power law. Is that really the principle?
That's pretty much it. Yeah, independent power law and sort of along with power law spanning several orders of magnitude. And there's like a little wiggle room in each of those things, but generally that's it. And so, with votes, not only do you violate the independence because, like for the presidential election, you're essentially two candidates, but also you have dependence on the number of people in the precinct, right? There's an upper limit on how many votes somebody can get.
Mhm.
And Benford will work in systems where there's technically an upper limit, but there's a lot of space to move around in terms of the values. But in elections, there's not that much room, and so you have dependence in a couple ways there, which makes it really hard for Benford to work.
I see. Thank you. Any other questions?
I will throw in, like, I'm not an expert on this. I talked a little bit with one of the faculty members who is, when I was doing all the election stuff. So you can use Benford on second digits. And I don't know it off the top of my head because I don't do any work on this, but there is a predicted distribution of the second significant digit in Benford. That's what they use to do election fraud detection. It's really hit or miss. So there are some people who try to do it and feel like they get some good signal, but there's a lot of false positives, like elections where we know there's not any fraud, but the second digit Benford analysis would suggest that there is. So the debate, like having read all of these papers in November, the debate is, so we know you can't do first significant digit for all the stuff I talked about. Second significant digit Benford doesn't have all of those conditions of independence and power laws necessarily. And so it's sort of more applicable in the situation, but it's also like not super reliable. So some people say it's irresponsible to even try to use it for elections because it's going to potentially flag something as fraudulent when there's no fraud. Like, we know there's no fraud. Other people are like really committed to using it and making it finer and finer in terms of what they look for. And again, they use it as one tool in a collection of statistics that they evaluate, but it's really sketchy even if you do it the right way to get reliable results in election fraud detection with Benford. It's just one of those places where it doesn't work that well.
Right. And I would also expect that the bigger issue with elections is not fraud in that people are not necessarily writing any votes. It would be people who are voting who are not supposed to, or more likely people who are uh, uh, being disenfranchised. And that's not really an issue. Enfranchisement is an issue in the U.S., but not necessarily people voting when they're not supposed to. Obviously, that's been well addressed. All right. Looks like we have one more question from Tyler Roost. What other aspects of misinformation do you think Benford's law may be useful to in terms of detecting? Also, in what ways do you think you will tackle the realm of problems in the future?
Yeah, it's a great question. In the social media space, I think part of what it can be useful for is looking at when is misinformation being amplified unfairly or fraudulently, let's say, right? So I come in and I tweet some conspiracy theory or just something that's like straight out wrong, and it gets 50,000 likes. Say I decide to say that like Keith murdered a puppy, and Keith says I didn't murder a puppy, and I say I have evidence that he did, and I have 50,000 likes on mine and a bunch of comments, and Keith doesn't get anything. I'm going to look more reliable in that case. And that, that's a strategy, especially the Russian state-controlled bots. We know a lot of their strategy was to essentially amplify and legitimize misinformation. And so that's the kind of thing where Benfords Law could be really useful. So you have a tweet, and the tweet may come from someone who's not a bot, right? Like a person who just wants to spread bad information, but it's being amplified by bots. So then you would have a tool that essentially goes to the tweet in question, as opposed to an account like the bot detectors are designed for now, goes to a tweet in question. It looks at the population of people who have interacted with that tweet, and then does a sort of Benford analysis on each of those people and gives you a picture, do the people who have interacted with this content look legitimate, or do they look majority fraudulent? Because you're going to have some of both. You'll have some real people and some fake ones. I think that's a really promising space to look at this. Essentially, is this being fraudulently amplified? So not looking at individual accounts. I mean, you kind of are, right? But you're using it to assess in pieces of content for fraudulent amplification. I think that's a really straightforward next step and would be a really fascinating thing to test. And like an easy experiment to run. Like, it'd take a while to do it, but it's very clear like how to proceed with that. And if it works, it's something that the platforms could develop. And Emilio, you probably know better than me. I mean, it's hard to get the kind of API access you need to, have a tool that adds on to be able to do all the queries that would be required for this. But it would be really useful, right? So I think that's a really interesting space for like looking at what comes next and using it to combat misinformation.
Great, thank you. And with that, I think there are no more questions. But for those who want to chat, we have a bunch of people chatting with Jen this afternoon. This is a great conversation as always, and we will talk to you later.
So
Great,
Jen,
thanks everybody.
yeah. Hi, Jen. This is Alma again.
Hey.
Hey, so at 3:30 your time and 12:30 our time, you will be meeting with Tyler. And that's a different link if you notice on the schedule that I send you. If you join like a minute or two before, I can give you host access. So I'll see you at that time.
Okay, thank you.
Okay, see you then. See you then.
Thanks everyone.
Awesome. Bye.
Bye.